We're going to start talking about partial derivatives. So first of all, let's try to present this notion in analogy to regular derivatives, ordinary derivatives for functions of one variable. Let's recall that for a function of one variable, the derivative represents the slope of the tangent to the graph at a given point. So if this is the graph of y is equal to f of x, and here's the point a comma f of a, then the tangent is the line that matches the graph in the best possible way around that point. And the slope of this line is what we denote by f prime of a, or df over dx for x equals a. That's the Leibniz notation. And actually, let's start with a function of two variables, f of xy. And let's define the partial derivative with respect to x at the point a, b. So what was the definition of the ordinary derivative for the function of one variable? So this was pretty much the limit as h tends to 0 of f of a plus h minus f of a divided by h. And in some sense, the idea behind this definition is that one takes the secant line between the points a comma f of a and a plus h comma f of a plus h. And as h tends to 0, that secant turns and pretty much becomes the tangent, with the consequence that the slope of the secant line will numerically approach the slope of the tangent line, which is the derivative that is the goal of that definition. So in the case of two variables, what we do is we really freeze one of the two variables. So here we freeze the variable y because we're trying to take the partial derivative with respect to x. So we freeze the variable y and we pretend that we have a function of just one variable, and we just pretty much imitate the derivative with respect to that one variable at the point a comma b, or since b has been frozen, at the number a. And we call this the partial derivative with respect to x at the point a, b. Now, this can be thought of as certainly representing a certain slope, but I think that it's much more useful to think of this as the rate of change of the function f of xy at the point a, b when the second variable y is kept frozen. So it might be a good idea to actually sketch the domain of definition of this function. So let's say that here's the point a, b, and our function is defined on this set. Then to realize what is going on here, we should just understand what it means to freeze b. To freeze b means to just take all points whose second coordinate is b, and they all lie on a horizontal line, and restrict the function on this segment. It then becomes a function of just the first variable, and we just take its derivative with respect to x. And obviously, one can have a very similar definition of the partial derivative with respect to y at the point a, b. So this will be the limit as h tends to 0. Now we freeze the first variable. So this becomes f of a, comma, b plus h minus f of ab over h. And that's the partial derivative with respect to y. It can be thought of as the rate of change of the function with respect to y when x is kept frozen at the point B. Now, in simple terms, how do we actually compute these derivatives? The idea is pretty simple. So first of all, in most cases, we will just use the ordinary differentiation. So let's say that we're given a function f of xy to be x squared y plus x cubed minus y squared. So let's take this function and let's ask ourselves what the partial derivative with respect to x of this function will be. And if we follow the definition that we gave, we will realize that y is being frozen as a variable, meaning we think of it as a constant. So what would be the derivative of this function that I just wrote if we thought of y as a constant? And the answer is, start with the first term. You have x squared y is a constant. So you will take the derivative of x squared, which is 2x, and you will just treat y as if it was a concrete constant number. So you just multiply the derivative by it. And then the derivative of x cubed is simply 3x squared. And now the other interesting thing is that the derivative of y squared, again, we said y is a constant. So what happens when you take the derivative? You will get 0. So there's nothing more to add. It might be useful at this point to pause the video and try to figure out the partial derivative with respect to y for yourselves, and then restart the video to see if you did the right thing. So what would be the partial derivative with respect to y? And here we see that the partial derivative with respect to y would be x squared times the derivative. Now x is treated as a constant, and we take the derivative of y, which is 1. The derivative of x cubed is 0, and the derivative of y squared is 2y, so minus 2y. And this is the partial derivative with respect to y. One of the interesting things here is that there is an alternative notation similar to the prime notation for functions of one variable. So instead of writing delta f over df over dx, actually, I never mentioned this, that you can think of this as a curly d. So you have a d that you curly tap like that and it becomes a curly d. Sometimes we call this partial. So we will say partial f over partial x. But the alternative notation is f sub x. And for the partial derivative with respect to y, the alternative notation would be f sub y. And of course, it should be noted here that this concept is not native to just 2 variables. We can have it for 3 variables, for 4, for 7, for as many variables as we like. So to do our next example, let's give ourselves the function f of x, y, z, which is x, y squared, z cubed over x minus y squared. And let's compute the partial with respect to x, the partial with respect to y, and the partial with respect to z. So again, it would be a good idea to stop the video and try to figure out what the partial derivatives are going to be by just using the quotient rule. In each of these 3 cases, you will have to freeze 2 variables, think of them as constants, and take the derivative with respect to the variable under consideration. Okay, so let's do it together now. So for the first partial derivative, we treat y and z as constants. So when we do so, the derivative of the numerator would be y squared z cubed times the denominator, which is x minus y squared, minus the numerator times the derivative of the denominator, which is simply 1. And then we divide by x minus y squared. Let's find out the partial with respect to y. So now the derivative of the numerator is going to be x times 2y z cubed. Notice how x and z are kept constant, times the denominator, minus the numerator, times the derivative of the denominator, which now is negative 2y, and divided by the denominator squared. And finally, with respect to z, now we have a much more interesting situation, because you can think of the whole quantity xy squared over x minus y squared as a constant, which makes this particular partial differentiation much more straightforward. So you can think of it as xy squared over x minus y squared times the derivative of z cubed, which is 3z squared. And these are the three partial derivatives. Okay. Now, there are interesting examples in which one can actually and should actually use the definition. For example, let's do one such example. So consider the function f of xy to be equal to xy over x squared plus y squared if x comma y is different from 0, 0, and 0 if x comma y is equal to 0, 0. When we looked at the two-path method, this was the function that we studied, and we saw that the limit of xy over x squared plus y squared doesn't even exist as xy tends to 0, 0. So you can see that no matter how we define that function at 0, 0, it can never be made to be a continuous function. But despite that fact, we will see that this function does have partial derivatives at 0, 0. So the partial derivative at 0, 0, by definition, would be the limit as h tends to 0 of f of 0 plus h, meaning h comma 0, minus f of 0, 0 over h. And let's see what we get. What is f of h comma 0 for h different from 0, of course? Well, you will have h times 0 over h squared plus 0 squared. To make a long story short, this whole thing here is 0, minus f of 0, 0, which is 0, over h. So you simply have the limit as h tends to 0 of the quantity 0 divided by h, which is simply 0. So the partial derivative in this case does exist, and it's equal to 0. And because of the symmetry of this function, so f of xy is the same thing as f of yx, we can very similarly find that the partial derivative of this function with respect to y is equal also to 0. So it's kind of interesting because we have a function which is not even continuous at the point 0, 0, yet it has partial derivatives at that point, which somehow suggests that the mere existence of partial derivatives at a given point cannot be in complete analogy with the existence of the ordinary derivative for a function of one variable, because existence of the ordinary derivative for functions of one variable meant that the function was also continuous. And here we have a discontinuous function that has partial derivatives. And, you know, there's a very simple way to explain why continuity is not needed for the existence of partial derivatives. And the reason is, if you think about it, so here we're interested at the point 0, 0, at this point, right? Ask yourselves, when you look at the partial derivatives, when you try to find the partial derivatives of a function at a given point, what are you looking at? What are you taking into consideration? And the answer is the values of the function on the horizontal line through that point and the vertical line through that point. That's the only thing that you're taking into consideration. So, in other words, the functions can be pretty monstrous here in this territory, and the partial derivatives at the specific point wouldn't even know about it. Okay, so you can have technically a function which is discontinuous at a given point, but does have partial derivatives at that point, and that's exactly what just happened with the example that we gave. So, as we're going to see a little later, we will have a much more genuine notion analogous to that of differentiability than just the mere existence of partial derivatives. That seems to be something pretty weak in some sense. Let's now go to another interesting situation. The fact that once we take partial derivatives, those will be functions, new functions. So it makes sense to take partial derivatives of partial derivatives. So, for example, if I have taken the partial derivative of f with respect to x, then it might make sense to try to take the partial derivative with respect to y of that. And the notation that we adopt for this, it looks like this. So we have a square on the partial on the top. And then I'm going to write first from the right to the left, first the partial with respect to x, then the partial with respect to y. However, if I am to follow the other notation where I had already taken the partial derivative with respect to x, and now I want to take the partial derivative with respect to y, then it makes perfect sense if I remove the parentheses to write it this way. So somehow we are compelled to adopt a different order for the notation of the order of differentiation in the case of higher order partial derivatives, as we're going to call them. So if we use the Leibniz notation, then we read the differentiation from the right to the left. If we use the subscript notation, then we read the differentiation from the left to the right. I mean, this cannot get more confusing. However, there is a very, very nice theorem that comes to our assistance here. And it says that under mild circumstances, mild conditions compared to what we usually face in this course. So in particular, we want the second order partial derivatives to exist and be continuous. But again, allow me to just write it in a rather vague way. So under mild conditions, and here, let's just put existence and continuity of second order partial derivatives. We have that the partial derivative with respect to first x and then y is the same as the partial derivative with respect to first y and then x. This is known as Clairaut's theorem from the French mathematician who was involved in finding this theorem. And it pretty much tells you that, as long as we deal with good enough functions, we can just relax our attention to the order in which the derivatives are being taken and completely disregard that order, because it doesn't really matter what the order with respect to which we're going to be taking these derivatives should be. Okay, so in some sense, normally you would have thought that if you have a function of two variables, you would have had partial derivative with respect to x twice, and partial derivative with respect to y twice, and partial derivative first with respect to x, then with respect to y, and then partial derivative with respect to first y and then x. But in truth, these two derivatives are the same. So you really have three partial derivatives. Sometimes we call the ones that are just with respect to x or just with respect to y pure derivatives, and the ones that are with respect to both variables mixed derivatives. So just to do a very, very simple example, let's just take this function, x cubed y minus x y squared, and let's compute all the second order partial derivatives. To do so, let's find the first order partial derivative. So we will have 3x squared y minus y squared. F sub y would be x cubed minus 2xy. And now fxx would be 6xy minus the derivative of y squared, which is 0. Fyy would be minus 2x. The derivative of x cubed will be 0. The derivative of negative 2xy would be simply negative 2x. And finally, fxy would be 6xy derivative of fxy would be 3x squared minus 2y. Okay, and you can easily notice that you would have found the same answer had you taken f sub y and differentiated with respect to x. So if you take f sub y and you differentiate it with respect to x, you're going to get exactly the same answer that we just got by differentiating the partial derivative with respect to y with respect to x. Okay, and that's our introduction to partial derivatives. We should say at this point that it would be a very useful task for anybody who sees partial differentiation for the first time to get a bunch of functions and try to take their partial derivatives by using the principle that we just explained, which is freeze all but one variable and differentiate with respect to the non-frozen variable. And that's all. Thanks for watching.